So now we're going to be looking at modeling with linear functions, and really what this means is that we're looking at word problems. Now, to approach word problems, there's lots of different strategies. Some of them are given in more detail, like this one from the textbook. There's a couple of other ones that are good starting points because they're simple and easy to remember, though they might not apply to exactly every single problem. And really, the key here is to practice and try to think about, first, following along with somebody else, which is what the next two videos are also going to do. But then also practicing on your own, working through some of the problems, and trying to identify what am I doing when I'm trying to figure these things out. So, something that's fairly common in whatever strategy is that you're identifying, things that are changing. Sketching a picture is something I would pretty much always do. You're reading the problem to identify important information. There's a lot of things that end up coming up again and again. When you're looking for things like slope or initial value, there will be hints that appear like in terms of the wording or in terms of the units that will tell you that this is a slope, or this is where your starting point is, or your y-intercept. And so getting some practice will help you find these things. I mean, I'll let you continue through and go through that problem-solving strategy. This is in more detail than some of the other ones that I might use, so it'll take some time to kind of work through it for yourself to know what it's suggesting that you do. So another one I might reference is from Essential University Physics, because I also teach the first year physics courses here at Mount A, or I'm one of the professors for the first year physics courses. And here they use a mnemonic that's really nice and simple, IDEA. So interpret the question. And so there you can look back at your problem-solving recipe that the pre-calculus book has to kind of make those connections between what does it mean, what's the steps that help me interpret it. Develop your equations. When it says evaluate, that's really just do the math. So once you have your equation or equations, then work with it to find the thing that you are looking for, and then assess. So in this case, does it make sense? Does your answer make sense? There's different ways to assess things. It might be, does it make sense? Does it apply in a certain situation? If I plug things back in, do I get the right results? But following this kind of step, it gives you at least a place to start when you're approaching these problems. Now, maybe you have your own experience and you have your own mnemonic. You don't have to follow the strategies that are listed in any of the documents that we give you, as long as you find something that works for you to help you approach these word problems or creating these mathematical models. So, for example, I made up a new one, Hydra, because I'm a sucker for superhero movies. And in this case, like there are certain hints, and so in the word problem that will tell you about the quantities that you're looking for. So, vocabulary that you might want to look for, or being familiar with which things are telling me what. So identify your variables. Draw a picture. I almost always draw a picture. And then relate things. And so this is where you're looking for relations. And I would say relations are equations. If I know something is twice as big as something else, or is always going to be twice as big as something else, say I'm looking at a fence that's in a rectangle, and one side is always twice as big as the other, I can say that the length is equal to 2 times the width. And that's one relationship, which gives me one equation. And then I kind of assume that you would then go through and do the math, and then again, looking back at your answer, does this make sense? So if you can find a mnemonic that helps you, go ahead and do that, either online or making it up yourself. I find visualizing is really key, certainly in physics. And if we're doing modeling, you're trying to model something in real life. Now, sometimes it's not a picture, maybe it's a graph, maybe it's a table of values that would help you, but like, having something else aside from just what the words say and the equations usually will help you, set up the equations. Now, when you're looking at linear problems, there's a few things I suggest, or that I might suggest as starting points. Questions to ask yourself when you're reading through it. So what thing depends on the value of another? When you have a linear equation, y is equal to mx plus b, the y value is the dependent variable that depends on the value of this independent variable x. Now, I know that sometimes it's not so clear-cut what thing is dependent on the other. It's really, in the context of the question, how much money am I going to make if I sell X amount of stuff? So the amount of money that you make, it depends on how many things you sell. But you could also ask, if I've made this much money, how many things did I sell? And in that case, you're kind of looking at the problem in the opposite way, like trying to figure out how many were sold given how much money you earned. So, what ends up being dependent and what ends up being independent can depend on it depends on the context. And so laying that out explicitly is a good idea just to help you get started on these problems. So is there something where there's a starting point, which means like the y-intercept, when your independent variable is 0, so at the start of the race, that would be t is equal to 0. Or before you sell, or anything in that other example, that would be your starting amount of money, say. So that would be a y, that's usually a y-intercept if you're using the starting point. Though they may also be saying, okay, at this point in time, 3 hours into the day, you have sold this, and at 5 hours you've sold that. So there, your starting points are not the y-intercept. There you're going to want to use 2 sets of coordinates. But if you're lucky, you may have been given just the y-intercept right away. Now, is there a rate of change? One of the hints that something is a rate of change is that you're saying like it's 1 unit divided by another. So if you're looking at how much money you earn for selling bricks, or maybe how much money you have to spend as you're building a wall. Well, there's so many dollars per brick that you end up using. So that is a rate of change. I am changing how much money I am having to spend depending on how many bricks I end up using. And then there are other key relationships that are important that help give you relationships like that in that relate part of things. Do you have 2 lines that are parallel or 2 lines that are perpendicular? Now, sometimes it might say that explicitly and sometimes it might not. Now, perpendicular lines, for example, we'll see in the next slide, those come about when you're looking at the shortest distance between, say, a point and another line. Or are you given an intersection point? Say, for example, when does one thing become more expensive than another? If you have the relationships for how much money you're having to spend for, say, a data plan, and you're comparing 2 different data plans, when one becomes bigger than the other, or just before it becomes bigger than the other, you have this intersection point. And that's where, for a particular x value, your y values are both exactly the same. So, again, these are just some places to start, and it really takes practice to know where to begin in different word problems. So one example of a word problem is here from the textbook. I think it's on page 135. And really what I'd like you to do is, before you look at what they've drawn, is just start with the word problem right here and see if you can answer that question before you go into the solutions. Like, the solutions keep going down. I've only just included the drawing that they have right here where they've defined a coordinate system. So when you're approaching these examples from the textbook, try to do them first, and then once you've run into problems and you have questions for yourself, then go back and see how did they approach this. Now, I also wanted to focus on a few things here. In this particular question, they have 2 lines of interest. There's this line right here, that depends on, well, I guess this is the distance east. And they also have this line right here, which is another road. So the blue road, or the blue line, is a road from Westboro to some other town, and the orange road is the line from Eastboro to that original road. And in here, in this problem, it explicitly says the second road, which is perpendicular to the first. Now, that's a key insight, and we'll get to what that means in just a second. So what you do have in this problem are two lines, and they're both dependent on the same x. So the first line, y1, or the height of that road at any particular point, depends on the slope times its position east, or your position to the east, plus the intercept, and that intercept seems to be at 0. And then you also have the second line, y2, where the height of that line depends on your position going to the east, away from Westboro. And then you have this slope intercept for that line as well. So two lines, and they both depend on the same x, the same independent variable. Now the relationships here, depending on what you can read out of the problem, if it's parallel, then you end up having that the slopes are equal. Two parallel lines, the slopes are equal. When they're perpendicular, you get this other funny relationship, and we'll look at that in a minute. So the second slope is the negative reciprocal, or the opposite to the reciprocal of the first line, the slope of the first line. So m2 is equal to minus 1 over m1. If we were to look at getting an intersection point, then you know that y2 is equal to y1. So those three relationships give you information that you can then pull out of the word problem. Now, just as a, not every time will you get the thing saying, or the word problem telling you that one line is perpendicular to another. But where this might come from is that if I consider a point that's right here, that's offset from some road in this particular place, and I want to make a junction. I want to build a road for the least amount of cost to meet up with that other road. Well, for the smallest cost, I'd need the smallest road. And what you'll notice is that if I do anything other than perpendicular, my line gets longer. So right here, I have an obtuse angle. If I were to look at that angle right there, if my line were up in this direction, I have an acute angle, and right here, I have that 90-degree angle. And the shortest road occurs when I have that 90-degree angle. Anything else, and my road will be longer. Okay, so I'm going to stop it here. I will give another advanced example about why we get that relationship for perpendicular lines. But when you look through the next two videos, I'd like you to, once the question gets posed, try to stop it and see if you can build the answer before you watch the rest of the video.